I want to start with something that sounds completely obvious. Light travels, right? You turn on a lamp, and the light goes from the bulb, hits the wall, you see the wall. Simple. Light traveled. We've known this for centuries. But here's what I want to do today. I want to look at that word travels very carefully. Because when you actually sit down and ask, what is traveling? What's the thing that's moving? You find yourself in the middle of one of the most beautiful and bizarre stories in all of physics. And I find that the things that seem the most obvious are almost always the things worth examining the hardest. So let's start with what your intuition probably tells you. You probably picture light as something like a wave in water. You throw a stone in a pond, you get ripples. The ripples move outward. That's traveling. Something is moving. Now for water waves, the water itself is moving. Not all the way across the pond, but up and down. The wave is a pattern of disturbance moving through the medium. The medium is the water. The wave pattern travels, the water stays more or less where it is. So naturally, people in the 1800s said, well, light must be like that. It's a wave. So there must be some medium it's waving in. They called it the ether. And this was a perfectly reasonable thing to think. Waves wave in something, right? So light waves must wave in something. And then came the experiment. Michelson and Millay, 1887. They built this beautiful instrument, an interferometer, where they could measure tiny differences in the speed of light in different directions. See, if there's an ether sitting there and the Earth is moving through it, then light going in the direction of Earth's motion should be a little slower than light going sideways to that motion, like rowing a boat upstream versus across a river. They measured this very carefully with the best instrument of its time, and they found nothing, no difference at all. That was the first shock. The ether wasn't there. Light wasn't waving in anything, it was waving in nothing. Now that alone should keep you up at night. What is oscillating if there's no medium? We'll come back to that. Then Maxwell had already given us the answer in a way, about 20 years earlier. Even though nobody fully appreciated what he was saying, Maxwell wrote down equations, 4 of them, the Maxwell equations. And from those equations he showed that electric fields and magnetic fields can sustain each other. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. And these two fields chase each other through empty space. And they do it at a specific speed, the speed of light. He calculated it just from the constants of electricity and magnetism. And he got 300,000 kilometers per second, exactly the speed of light. And he wrote, essentially, it seems, we may conclude that light is an electromagnetic disturbance. Now this is already strange. What's oscillating is not matter. What's oscillating is the field. An electric field and a magnetic field oscillating perpendicular to each other, perpendicular to the direction of travel, chasing each other through space at 300,000 kilometers per second. Nothing material is moving forward. The disturbance is moving forward. The field values are changing. No substance is being carried along. But then, and here it gets really interesting, Einstein comes along in 1905, and he says something that at first sounds like a cleanup job, but is actually a revolution. He says the speed of light is the same for all observers, no matter how fast they're moving. You can be standing still, I can be on a rocket going half the speed of light. We both measure a beam of light going exactly, c, 299,792,458 meters per second. No difference, none. This is not intuitive. If I throw a baseball at 90 miles per hour and you're driving toward me at 60 miles per hour, you measure the ball coming at 150 miles per hour. That's just addition, that's Galileo. That's how normal things work. But light does not do that. You can be running toward a beam of light and it still comes at you at exactly the same speed, always, under all circumstances. And what this means, and Einstein saw this, is that space and time are not separate, independent things the way we thought. They are linked. They are parts of one thing, space-time. And when you start moving, space and time trade into each other. in a way that keeps the speed of light constant for everyone. Time slows down for moving observers. Lengths contract. This isn't science fiction. It's measured every day in particle accelerators. The moon, created in the upper atmosphere, should decay before they reach the ground. They don't make it by classical calculation, but they do reach the ground because time runs slow for them. We measure it. Now, from the point of view of the photon itself, this gets wild. From the photon's own reference frame, if you could ride along with a photon, which you can't, but just as a thought experiment, time does not pass at all. The photon leaves the sun, travels 93 million miles to Earth, takes 8 minutes by our clocks, and for the photon, those 8 minutes are 0. It is emitted and absorbed instantaneously. The distance it travels from its own perspective is 0. It doesn't experience travel at all. It doesn't experience anything. It blinks out of one place and into another with no time in between. I find that extraordinary. We say the light traveled, but from light's perspective, there was no journey. Now here's where I have to tell you something important about what I said, and what I always say, and what every honest physicist has to say. When I described the photon's perspective, I was being sloppy because the word perspective implies an observer, and a photon has no mass. And special relativity breaks down when you try to transform to the reference frame of something with no mass. You can't actually ride along with a photon. The math doesn't let you. So when I say from the photon's perspective, I'm extrapolating something that the mathematics hints at but doesn't fully allow. That's an important distinction. Physics is about what the equations say, not about the stories we tell about the equations. The stories are useful, but they're not the same as the physics. Okay, so we've established light is an electromagnetic wave. It travels through empty space with nothing material moving, and it travels at a speed that is constant for all observers. And in its own frame, if we loosely use that term, no time passes. But now I want to get into the part that I find the most beautiful and the most disturbing, which is what quantum mechanics says about all this. By the early 20th century, something was bothering people. Specifically, it was the photoelectric effect. You shine light on a metal surface and electrons come flying out. Fine. But here's the thing. The energy of the electrons that come out does not depend on the brightness of the light. It depends on the frequency, the color of the light. Bright red light ejects no electrons at all. Dim blue light ejects electrons just fine. A wave picture cannot explain this. If light is a wave, then brighter light means more energy, and you'd expect brighter light to kick out electrons harder. But that's not what happens. Einstein in 1905, the same year as special relativity, an extraordinary year for him, says light comes in packets, quantized chunks. Each packet has an energy that depends on its frequency. E equals h star nu. H is Planck's constant. Nu is the frequency. A single packet has enough energy to kick out an electron, or it doesn't. More brightness just means more packets, not more energy per packet. If each packet isn't energetic enough, no electron comes out. No matter how many packets you throw, those packets, we now call them photons. And this is where the story gets genuinely strange, because now light is not just a wave, it's also particles, discrete lumps. You can detect them one at a time. A very dim light source fires photons one at a time. And if you have a sensitive enough detector, you hear click, 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 individual events, individual lumps of energy arriving, not a continuous flow, clicks. But here's the disturbing thing. If you take those individual photons one at a time and you shine them through two slits, you know the famous double slit experiment? Each photon somehow goes through both slits at once. Because when you look at where they land, even one photon at a time, over time, you build up an interference pattern, a bands, an alternating pattern of where photons land and where they don't, which is exactly what you'd get if waves were going through both slits and interfering with each other. But we're sending one photon at a time. There's nothing to interfere with. A photon is interfering with itself. And if you put a detector at the slits, trying to catch which slit the photon actually went through, the interference pattern disappears. The photon now goes through one slit or the other like a normal particle, and you get two piles instead of a wave pattern. The act of finding out which slit it went through destroys the interference. This drove Einstein crazy. He never accepted it. He thought there had to be a deeper explanation. He thought God doesn't play dice. And yet the theory works. It predicts everything we measure. It predicts it with more precision than any other theory in the history of science. Quantum electrodynamics, the quantum theory of light and matter, is the most precisely tested theory in physics. Its predictions have been confirmed to 10 decimal places. So what is light really? Is it a wave or a particle? And here I want to tell you something that I once said, and I'll say it again because I think it's important. It is neither. It is something for which we do not have a good word, and we do not have a good classical picture. The word wave and the word particle are both human inventions based on human experience of large classical objects, water waves, billiard balls. Nature at the quantum level is not obligated to fit those words. It does its own thing. It is light-like, which is its own category. What we have is a mathematical framework, probability amplitudes, complex numbers, wave functions, that correctly tells us the probability of finding a photon at any given place and time. The wave function is a wave. It has frequency wavelength, and it interferes with itself. But when we actually detect a photon, we detect it at a definite location as a particle. Where the wave function has large amplitude, we're more likely to find it. Where the wave function has small amplitude, we're less likely. And when we detect it, when someone looks, when a detector clicks, the wave function collapses to that point. Now, I need to tell you something about this picture that I find the most mind-bending of all. In my lectures on quantum electrodynamics, I described how a photon gets from point A to point B. And the honest picture, the quantum mechanically correct picture, is this. The photon doesn't just go in a straight line. It goes along every possible path, every single possible path from A to B, simultaneously, through completely wrong paths, curved paths, zigzag paths, paths that go out to Jupiter and come back. All of them. Each path contributes a little arrow, an amplitude. And you add up all the arrows. Most of them cancel each other out because nearby paths point in random directions and they average to zero. But the paths near the classical straight line path, near the path of minimum time, those don't cancel. Those arrows happen to all point roughly in the same direction. So they add up to give a big total contribution. And the result is that the photon overwhelmingly behaves as if it went in a straight line, because that's where all the contributions add together without canceling. This is called the path integral formulation, and it tells you something profound. The classical picture, light goes in straight lines, isn't a rule that light follows. It's the emergent result of quantum mechanics, where all the wild quantum paths cancel and only the classical path survives. The law of reflection, the law of refraction, the straight line propagation of light, all of it comes out of this. Light going in a straight line is not a fundamental law. It's what happens when you add up all the arrows. Now let me bring this all together because I want to be honest with you about what we know. And what we don't know, we know that something propagates from a source to a detector. We know it goes at a fixed speed, a cc, in a vacuum, for all observers. We know that what propagates has wave properties. It has a frequency, a wavelength. It interferes with itself. We know it has particle properties. It arrives in discrete lumps, clicks in a detector, carries a definite energy equal to h times its frequency. We know that a photon has zero mass, and because of that, it can only travel at the speed of light, never slower never faster, in vacuum. We know that from a relativistic point of view, the photon's proper time is 0. It doesn't age. It doesn't experience duration. What we do not know, what I will not pretend to tell you, is what is really happening in between emission and detection. What is the photon doing when nobody's looking? Is the wave real? Is the particle real? Is there a trajectory at all? These questions, and I want to be clear about this, these questions may not be meaningful. They may not have answers, because the answers we get depend on how we ask the question, on what apparatus we set up. Nature is not secretly doing one thing and hiding it from us. The question, which slit did it really go through, may simply not have an answer when we don't look. That's not a failure of our knowledge. That may be a feature of reality itself. And this is what I mean when I say that nobody understands quantum mechanics. Not because the equations are confusing, and they're not really, but because the equations don't give you a story, they give you a calculation. You put in your question, you get out your probability, and the probabilities are right. But if you ask what's happening in between, you don't get an answer, you get philosophy. And I'm always suspicious of philosophy where physics should be. So here's the reality check that I wanted to give you. Light travels? Yes. 300,000 kilometers per second? Yes. Is it a wave? Yes. Is it particles? Yes. Is something physical moving? Well, the field values change. The electric and magnetic fields oscillate, but no material substance is transported. Is time passing during the journey? Not from the photon's reference frame, which we can't quite take properly. But in the limit, no time passes. Does the photon take a straight line in the sense that adds up correctly in quantum mechanics? Yes, but only because all the other paths cancel out. And what is light? It is a quantum of the electromagnetic field. A photon, something that is wave-like and particle-like and neither, that travels without a medium, that goes at the only speed it's allowed to go, that takes all paths simultaneously and mostly cancels itself out, and that arrives as a click. That's what traveling looks like when nature does it. And I think that's more interesting than the simple answer. Don't you?